Nobody wants to hear me go back through step by step by step by step. But I do want you to carefully look at my work because of a couple things. The way that I meticulously showed you what I'm plugging in. This is the level of work that we need you showing if you want full credit for the things that you do. So, for number one, I solved it two ways. Here I used the formula, and here I used 1/2 base times height. I gotta tell you, I'm a 1/2 base times height kind of person. I'm not a formula person. I can't memorize things. I struggle at memorizing. It's not one of my talents. I'm a concept person. I understand ideas, but I'm not good at memorizing like phone numbers and stuff like that. I struggle. I have to come up with little patterns or games or songs or something. So I work very hard at limiting the stuff that counts on my memorization because I'm sunk if I have to memorize too much. So I'm okay with 1/2 base times height, and even if I end up, I don't know, we might have to look at what do you think was more work? Using the formula or 1/2 base times height? I don't know, it's 50-50 kind of. Making sure that you have your units squared. Something important for you to know, and I want you to think about this carefully. If you want to get a pencil or color pencil from your basket, or make sure you understand this, your base is wherever the altitude is touching. So when you're using 1/2 base times height, in any triangle, your base is going to be where the altitude is touching, where the altitude is touching, where the altitude is touching. Not a big problem when we're dealing with equilateral triangles, but when you're talking about 1/2 base times height here, you need to know that your base is where your altitude is touching. Now we know with that triangle, I can draw 3 different altitudes. If it's an equilateral triangle, they're all the same because it's equilateral. But once I move beyond an equilateral triangle, I can draw a base from each vertex. And if it's an obtuse triangle, at least one of those altitudes is going to be outside of the triangle. So when you draw an altitude from the vertex to an opposite side, any opposite side, you want to make sure that that's at that right angle, and then that side becomes your base. So some kids were struggling with where their base is. When I get to these problems down here, I count on those 2 theorems where if you have congruent shapes, then the area of one is the same as the area of the other. And I can count on this shape being the sum of all the non-overlapping parts. And I sure do love those hexagons. Aren't they so much easier? Because those hexagons go into equilateral triangles. And they're a ton easier. Questions on the front page. Stuff you don't understand. Ziva, go ahead. The second question, this one? This one. Okay. So when we had to find the area, this equilateral triangle is the same as if I turned it, right? So my base is, and I could have drawn my base any way that I wanted. So this side here is half of the base. So when I went ahead and I figured out this side, I knew that it was a 30, 60, 90 triangle because this is 30. So I knew that this side here was going to be this short leg times square root of 3. Here's my x root 3. Do you see it here? Here's my side length times root 3. When I'm multiplying radicals, root 7 times root 3 is root 21. So this height here is going to be this 2 root 21. Does that make better sense now? Say that one more time. Yeah. So, okay. So when I want to find the area of the triangle, my area formula is 1/2 base times height. Here's my 1/2. My base of the triangle is here. And I know that that has a measure of 4 roots of 7. My height came from here. That's 2 roots of 21. So now when I go to multiply, 1/2 and 2 go away. 1/2 of 2 is 1. So here's my 4. And here I have 7. And I broke 21 down into 7 and 3. And then this becomes a double factor that can come out of the radical sign. So here's my 4 times my 7. And root 3 is left behind. Does that make better sense now? Okay. Olivia, what's up?
For number 5 on the, isn't the area 6.62? Because it's like a round.
Isn't that what I have? 6.62?
No, wouldn't it be 6.63? Sorry.
I don't know. Let's, so you know I like to keep my values in my calculator. So if I had to do the sine of 37 is equal to x over 4. So let's check out those calculations. So the sine of 37 times 4 gives me that. And then when I go ahead and I plug that in towards 1, so that's going to be the measure of my height, right? So my my area is 1/2 times my base times, and my height was this here. So I can just move up on the calculator and enter that in. So I get 6.62. And that's just because I like to keep these values in my calculator.
If I didn't keep my values in the calculator and got this area, would you mark it wrong?
So if you're off by 1/100th, I'm probably going to grab my calculator and do the calculations and then double check you. You're at the point now where just about what you're taking for the rest of the year is multiple choice tests. So then that rounding is not going to be necessarily as big of a conversation. Always take a peekaboo at the answers and see. You're like, okay, what do they want from me now? If it's a multiple choice test, that 1/100th isn't going to be a big deal. All right, anything else on the front we want to talk about? Okay, so let's talk about the back. Find the area of each regular polygon once they tell us it's regular. And again, we're in hexagon world, so this is tons of fun. Hey, this square one, don't be overwhelmed. I kind of geeked out a little bit. You didn't have to do all 3 of these, but I'm curious how you went ahead and found the area. Because if it's a square, I could have just done, once I figured out that the side length was 8 roots of 2, I could have just done length times width, the area of a square, side square. So that was my first choice that I did for number 1. Because these here, this here is an isosceles triangle, right? Isn't this going to be a 45, 45, 90 isosceles right triangle? So if my sides are 8, then I know my hypotenuse is 8 roots of 2, and that hypotenuse happens to be the side of the square. So length times width is just side squared. Thumbs up if you found the area that way. Anybody? Anybody? Okay, a couple. All right. Choice 2 was I went ahead and I found the area of the triangle. 1/2 base times height. And what's interesting is if you did an apothem here, you can do 1/2, here's your base, here's your height times 4. You could have also done this base times this height, 1/2 this base times this height times 4. And you would have ended up, again, with the same. So even 2 has 2 different methods to it. 3, oh, thumbs up if you did option 2, triangles, 4 times 1/2 base times height. Okay. Option 3 was a square is a rhombus. So I could have done 1/2 times the product of the diagonals. And if this diagonal is 8, so if this piece of the diagonal is 8, I know so is this one because it's parallelogram. Parallelograms have bisected diagonals. And I know this diagonal is congruent because it's a rectangle, and rectangles have congruent diagonals. So it also is a rhombus. So that square is a rectangle, a rhombus, and a parallelogram. So I can go ahead and multiply the diagonals and take 1/2 of that. And again, I get 128. Thumbs up if you did it that way. Option 3. Okay. So like I said, I kind of geeked out because option 2 even has another way of doing it. This is if I kept the triangles and I used this as a base, and I found this is my height. But my other way of doing this was if I did area is equal to 1/2, I can talk about each of these triangles have a base times a height here of my base times my height times 4. And I still would have ended up with the same. So there's actually 4 different ways of finding the area to number 4. Hey, you only have to do one. But like I said, I kind of geeked out while I was working on it because I was like, whoa, I wonder what they're going to do. So again, another hexagon and another hexagon. We sure do love those hexagons, don't we? And you were missing that hexagon when you came down here and had a pentagon. So when I found the area of my base, I knew that I had, and I have this habit of drawing my bigger triangle over here, and that helps me a lot. I've tried to draw the triangle inside the shape, even if the shape is a nice big picture, and I still don't like it. I always need to separate it out. Okay, we're gonna draw that. And then once I know it's 36, and then I went ahead and I was surprised when this came out. And then I looked at it, I'm like, duh, they gave me the answer. So I didn't need to do any trig there because they gave me the length of my apothem. Did you notice that? So then, okay, so my area, my triangle is 1/2 of my base times my height. They gave it to me, thank you. Times 5, because I'm going to have 5 of those triangles. So my area, my base, is 200 centimeters. And then when I talk about that area of the base, I want you to think about having 20 layers of that base going up. And this picture is a wacky one to me. Do you ever do that thing where your eyes play tricks on you and you can see it whether it's leaning towards you or away from you or standing up or leaning down? But you can go ahead and say that there are, if this is my base, I can talk about all these other layers of the bases that I can stack on top of each other. So here's one layer, and then here would be another layer. And I can repeat this 20 times, right? And that's why my volume, what is your capacity? 20 times 200, 4,000 cubic centimeters. Down here, same exact conversation except for this guy. That's the only thing that's different. We're going to go ahead and find the area of the base. We're going to multiply it by the height. And I know that this is the height because of this lovely right angle here. And then I know, think about what we did when we had our cylinder of our popcorn and our cone scooper, right? 3 of those cones would equal 1 snack. Questions on the homework? So simplest radical form, I guess you're right, it says that, doesn't it? So if I wanted to do this one in simplest radical form, I would have to do 1/2 of 6 is 3. 3 times 11 is 33. 33 times 5.5. Oops, not that. 33 times 5.5 is going to be equal to, this answer would then be 181.5 roots of 3. Do you like that better? Yeah? All right, and then over here, 1/2 of 6 is 3. Is this is a 32, right? So 3 times 32 times 16 is 1,536 roots of 3. You like that better? You want a Smarty for that? Go ahead.
Well, that fills it out.
Does that fill it out? I get to give you candy. That's the best thing. All right. Any other questions I can help you out with? Okay. So past the about when we talk about similarity, we know that similar figures means same shape, but not necessarily the same size. So your size is going to be either a reduction or an enlargement, depending on what you have. If your scale factor, just as a reminder, if your scale factor is greater than 1, that's when you end up with an enlargement. And if your scale factor is less than 1, that's when you end up with a reduction. When we talked about transformations, we talked about dilations. Think of a dial, you can turn it up or turn it down. If you make something bigger, it's an enlargement. If you make something smaller, it's a reduction. All right, so when we talk about similar figures, which we were doing with triangles and whatnot, we can talk about two-dimensional shapes with all corresponding angles congruent and a constant proportion between the lengths of every side. So this is no problem. This is what we talked about in unit 6, where we talked about similar triangles. Two-dimensional shapes. 2 dimensions means I have 2 measurements, a length and a width, right? No big deal. When I talk about a similar solid, I'm talking about a 3D shapes that are all the same type of solid and all corresponding lengths are proportional. So if I have a similar solid, when we talk about the same type of solid, I'm talking about prisms to prisms, pyramids to pyramids, rectangular prisms to rectangular, cylinders to cylinders. So they have to be the same type of solid, and then all the corresponding lengths are going to be proportional. Okay. So here we have 4 sets of shapes too, and we have to justify what we say as far as whether or not these shapes are going to be similar. So do me a favor, talk with your group mates and have some conversations about, do you think, which of these pairs do you think are similar solids? On your mark, get set, go. So let's talk about A. They look the same. Don't they look the same? Are they in proportion?
No.
How come?
It's because 5 we have a different fraction from 8 and 6.
You are correct. So
By like 1.
these are a no, because my height has a relationship of 8 to 6, and my bases have a relationship of 5 to 3, and they're not the same. So we're going to say no to them. All right, how about these? So my heights have a story of 14 to 7, and my bases have a story of 10 to 5 and 6 to 3. So they all simplify to 2 to 1. So this is a yes. And meanwhile, you have to check every single measurement. So these might look like square pyramids to you, but they're not. What are they? They're rectangular pyramids. How come?
Because of the sides.
Yeah, these bases don't have that base doesn't have the same measurement for a length and a width. All right, how about our cylinders?
Yes. Because the 5 on the small one is that diameter.
The 5 on the small one is the diameter, which means this diameter is a 10. So we have a 5 to 10. And then we have 7.5 to 15. So we're going to go with yes to this one. How about this guy? So we compare 4 to 10, and we compare 3 to 5. And those are not going to be the same. If this one was 2 to 5, it would be good. But this one is a no. So once you take a look at this chart, and I go back and forth on how to do this with you, to fill out the chart and then show you, or show you and then fill out the chart. So we'll try filling out the chart and then I'll show you. So you have the data, okay? If I have a similarity between my one dimension, which is my length, or we know it as the perimeter, the ratio of their surface areas is going to be 4 to 9. What is the relationship between 2 to 3 and 4 to 9? So what do you notice? Squares. So this is our values are squares. And remember, we're measuring it in units squared. If I have a one-dimensional relationship of 2 to 3, a surface area relationship of 4 to 9, I'm going to have a volume relationship of 8 to 27. What did I do?
Multiply
I cubed. Make sure you understand these notes. If two similar solids have a scale factor of A to B, their corresponding areas have a ratio of A squared to B squared, and their volumes are A cubed to B cubed. So if you have these boxes where I have this volume and this volume, I can know that this volume was a result of a 3 by 3 by 3 cube. And I know that the volume of 216 was a 6 by 6 by 6 cube. How did I get those numbers? I took the cube root of the volume to get the length ratio. So I know that I have a 3 to 6 or a 1 to 2 story. So I know that their surface areas would be in the proportion of 1 to 4, which is exactly what we had with our cubes. So because their linear lengths are 1 to 2, I know that their surface areas are going to be 1 to 4. I got that because their volumes were 27 to 216. All right, let's fill in the rest of the chart. If I know that my surface areas are 25 to 64, take the square root of those to get your linear lengths. What's the relationship between my linear? 5 to 8. If I want to know the ratio of my volumes, I'm going to have to cube 5. And I'm going to have to cube 8. 512. Now here's the deal. You have to go back to your linear length to get to areas or volumes. So notice from the volume we went to linear and then we went to area. So you're going to have to continue to come back to this linear length in order to figure out your areas or your volumes. When I'm looking at 27 and 64, in case you forgot where your cubed root feature was on your calculator, you go to math. And once you're in math, choice 4 is going to be the cube root. And then you type in cube root of 27 is 3. Math. Down to choice 4, cube root of 64 is 4. So I know that here I have a 3 to 4 story. So what gets filled in on this box here? 9 to 16. Kind of cool, right? All right. On the back here is a true story. So my husband and I bought our house, and it needed new carpeting in the kids' bedrooms, and it was tight on a budget. And I saw an ad in the newspaper that said you could carpet a room 10 by 12 feet. That's $216. I'm like, $216? We can afford that easy. So just so we're all on the same page, 10 by 12 feet is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Go into that box. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So basically from matinee to the corner of the room. That's 10 by 12. So I said to Mr. Glacier, like, honestly, we had a living room that was 20 by 24. So I was like, it's $400. We can afford that. He's like, it's not. I'm like, yeah, it is. Because the ad says that when you come back from lunch, we'll talk about how much it costs to carpet my room. So here we go. I want to carpet a room that measures 40 by 48. An advertisement states the cost to carpet a room that measures 10 by 12 is $216, but it's a reasonable cost for the room. So if I know that there's a 1 to 4 story between, this is what the ad says, right? A 12 by 10 room, and this is the cost that I have. I know that the area that I'm carpeting is 4 times bigger. Are you okay with that? So I start doing some math, thinking that I know what I'm doing, and I'm like, okay, if it's $216 for this, wouldn't this be 4 times more? Doesn't that make sense to you? But again, I'm going to say to you, I trust the math. Let's do it the way that we know. So if I know that it's $216, I know that it's $216 per 120 square feet. You okay with that? So when I divide that, 216 divided by 120, I know that this is $1.80 per 1 foot. That's the cost of my carpeting. So now what I need to do is figure out how much area is here.
Boring.
Not boring at all.
Just kidding.
Hold on a minute.
All right. So let's figure this out. So 48 times 40, I know that I actually have, for the square footage of my room, I've got 1,920 square feet for my room. And if I go to multiply that by $1.80 per square foot, check out how much money I'm spending on carpeting. What? What happened to $864? $3,000? And I was like, wait, what? How much is this going to cost me? That's crazy. Because the proportion is not 1 to 4, it's 1 to 16 for their areas. So this is 4 times bigger, but guess what? So is this. So this measurement is times 4, and this measurement is times 4. That's where the 16 comes from. So if I thought it was going to be $864, go ahead and multiply that by 4, because I need to multiply that by 4 again. And what do you get when you multiply it by 4 again? Yeah. So meanwhile, it would have been fine if only one of my dimensions was times 4, but they're both growing by 4. So I need to make sure that I multiply my original cost not by 4, but by 4 squared, or 16. Kind of cool, right? All right, so a park has 2 gazebos. The floor of each gazebo has the shape of a regular hexagon. The floor of one gazebo has a perimeter of 72 and an area of that. The floor of the larger gazebo has a perimeter. Find its area. Talk to your partner. Go. All right, so let's talk about what I did. My one-dimensional relationship is 72 to 96. Because that's my perimeter. Perimeter is my one dimension, right? So here's the fastest way I know to get that scale factor. 72 divided by 96, math frac enter. So that's a 3 to 4 story. So that should be quick. The ratio of small to big is 3 to 4. You okay with that? Okay. Now I'm going to think about my chart. And if you do this every time, you're not going to go wrong. Because if my one-dimensional relationship is 3 to 4, that's my A to B. My two-dimensional relationship is A squared to B squared. So that means it's 9 to 16. So if I'm talking about their areas, I'm not going to use a 3 to 4 scale factor. I'm going to use a 9 to 16 scale factor. So when I do that, here's my scale factor of my areas, and I set up my proportion. My small to big, this is what I'm looking for, is equal to my small to big. I'm not using 3 to 4 because that's my 1D story.
Couldn't you also just find the area like you normally would? Because they give you the perimeter, and it's regular. So.
Sure. Absolutely. Did you get the same exact answer? I love it. All right. So let's talk about cylinders A and B. Cylinders A and B are similar with a scale factor of 2 to 5. That's their 1D story is 2 to 5. Find the surface area and volume of cylinder B, given that the surface area of cylinder A is 96 pi square feet and the volume is 128. So talk about this first with your partner. If this is A to B, what are you going to fill in here? And what are you going to fill in here? Because this is what you're going to use to set up your proportions. And your mark is set, talk, think, go. So when I look at my 1D, 2D, and 3D stories, if I have a 2 to 5 story linear, I have a 4 to 25 story for area, and an 8 to 125 story for volume. So when I take what values I know, surface area of 96 pi, volume of 128 pi, I'm going to set it equal to this scale factor that fits the story. This is for area, and this one is for volume. So then solving for x is going to be did you get for our area 600 pi And for our volume, $2,000 pi. Does that sound right? When you solve those proportions, that's going to be what you get. So this is an interesting story. These two cones are similar, and we need to find the scale factor. So again, make your chart 1D, 2 dimensions, and 3 dimensions. If these are their volumes and you're given that they're similar, where can I put this story? Under my 3D column. What now? Take the cube root of both of them. The cube root of 108. So, interesting thing about what cube root of 108, that's not a perfect cube, is it? 256 is, though, isn't it? Nope, that's a perfect square. Let's go ahead and simplify it. When I talk about 108, 108, I know for sure, I'm thinking that's 9 and 12, right? 108 is 9 times 12, 9 is 3 and 3, 12 is 3 and 4. So the cube root is going to be 3 times the cube root of 4. I need 3 to come out and simplify. $256 is 16 squared. So here I have a 4 and a 4, a 4 and a 4. So this one is 4 cube roots of 4. That's our scale factor. So when you simplify a cube root, you're looking for 3 that can come out of the radical. And then what's left inside? So watch this. 3 times the cube root of 4 over 4 times the cube root of 4. Do you see how these cancel out? So my scale factor is 3 to 4. Their two-dimensional area proportion, 9 to 16. And I can say that this is 27 to 64. That's their volumes. Take the cube roots. All right, here's our punch bowl story. 2 punch bowls are similar with a scale factor of 2 to 3. So here's one punch bowl, and here's the other one. Let's talk about diameter, 2 feet. Punch bowls. You okay with that? Our one-dimensional story is 2 to 3. What's our two-dimensional story? What's our three-dimensional story? You get pretty good at your perfect cubes. 2 cubed is 8, 3 cubed, 27. All right, now that I have that story down, it says the amount of concentrate to be added is proportional to the volume. How much concentrate does the small bowl require if the large bowl requires 48 ounces? Which of these scale factors do I use? The volume one. So I know that 8 to 27 is going to be equal to some mystery compared to 48. Sound okay? So we go ahead and solve that proportion by using cross products. X is equal to about 14.22 ounces. 128/9 is my actual answer. So my advice for you is every time you're dealing with similar areas, similar volumes, make your chart. Ask yourself, which is my relationship that I'm talking about? And then that's the one that you use. All right. We asked you to work on a transformation packet. And when I see you next, we're going to go over the rest of that transformation packet. The key will be on Schoology. Here's some transformation practice for you. Any questions that you have, bring next class. I feel like I keep begging you to do your homework. I've said it before and I'll say it again. You've run a good race. Don't trip the finish line. Keep up with the work. Hold on a minute, Lydia. So, if you look at the calendar, we don't have a lot of time left. But you need to make sure that you're ready for this unit test. So we'll make sure we put it down. Here's your Geo unit test. So we have next class, and then we have a review, and then we have our test. So our next class is when we're going to review circles, answer your transformation questions, and then a review and a test. What's on your mind? Say that one more time.